share the screen. So folks, the topic today is neural networks as universal approximators. If you recall, last time I mentioned that neural networks are extraordinarily effective in solving a whole variety of problems. And I said that one of the reasons, or among the reasons that we do understand on why they are so effective, one is that they are universal approximators. Now, what are universal approximators and how are neural networks that? We'll see in a moment, in a short time. And today, the way we'll proceed is we'll do a little bit of theory, but a lot of lab. Are you together? We'll see things in action, or we'll see things in code. The language of choice here is Python. We will do it in Python. Now, if you're not very familiar with Python, do not worry. What I have done is, in order to make it easier to get started, most of the things I have made it into pre-built library. So you just have to call one or two lines on it. Right? And as you develop skills with it, then your job would be to go and make much deeper modifications to the code and extensions to the code and do the lab. But the first one will be very simple. Now, a recap of what we did in the last session, just looking at what I taught in the last session from the video, watching the video myself, we talked about the history of AI. AI has deep roots. It started, I mean, if you look at human aspiration to create intelligent things, intelligent beings, right? It goes back at least to 800 BC. We have evidence of the Hipparchus, Greece, myth of Hipparchus in Greece. Fast forward to after jumping through many things, for example, golems, part of the Hebrew tradition, we talked about Turing, Alan Turing's dream of creating intelligent machines, artificial intelligence. And the term itself, artificial intelligence, was of much more recent coinage, very, very recent, as in 1956. And the math behind it, though, quite a bit of the math behind it was actually developed in the 1700s and the 1800s. So it also goes to show that this subject is not something, it's not like yet another new programming language that has come up, right, with a completely new syntax. We are talking about a deep well of intellectual knowledge, intellectual initiative and ideas and concepts. They go back to 300 years. One of the things that you will learn about, and I'll talk briefly about, is called linear regression. I'll explain the concept of that. The person who created the loss function, remember I talked about loss function, that a lot of machine learning is about loss function. I'll reintroduce that topic. But the person who wrote down the loss function to solve was no other than Carl Friedrich Gauss, son of a coal miner who grew up to be a great mathematician, one of the greatest mathematicians, and indeed is often called the prince of mathematics, for good reason. In mathematics, you have had many towering geniuses, people like Gauss, Euler, etc., etc. And it's hard to compare them, of course. Each of them have been towering. Much of the calculus, much of the coordinate geometry, trigonometry, etc., that we have studied in the 21st century, in our 20th century, in our college textbooks, actually dates back to that time and to these great people, a lot of these Fourier and so forth. So these are towering giants, and this is something that people perhaps don't realize how deep the mathematical ideas behind all this goes. Foundations. Of course, Gauss was probably not trying to create artificial intelligence. He was trying to solve practical problems. And much of AI is used to solve practical problems. Right? It's used to make predictions, very much like Gauss was trying to make So we talked about Galton and so forth. We won't talk about that. It's that. Now, we also alluded to the fact that what is intelligence? It's a little, if you think of it as thinking machines, like thinking, then you're lost because thinking is not understood. It's certainly not measurable. And so we think in terms of learning. Machines can learn. And how can they learn? Because we can talk in terms of error and the reduction in error. But today, that error, often or more broadly, a more general term, is a loss function. The loss function, you will see it in action. All of these ideas, big ideas, will become very real for some very simple problems. Today is your first lab, so we will take baby steps. And it is going to pick up. So be warned, the whole thing will start picking up. Now, a lot of the ideas in this field come also, obviously, from a statistical tradition, lots of statistical mechanics, maths, which is again a part of mathematics. It comes from physics. It comes from computer science itself, per se. Many, many good ideas. Now, I mentioned to you what we understand about neural networks. I said that the neural networks are made up of linear transformations and deformations, alternating with each other. Today, I'll make it a little bit more concrete what these things mean, right? And we talked about gradient descent. I would like to, at some point today, show you gradient descent in action. These are very elemental stuff, but it is worth seeing this in action. And I believe I did show you gradient descent on the loss landscape, but we'll do it ourselves, writing our own code. We'll talk about back propagation and so forth, but for that, perhaps not today. That will come in the next session. Today, we'll learn, what is it that we'll learn about? We'll learn about this property of neural networks to be universal approximators. Are we together? First, we will see it in action, and then we will understand, or I'll give you some intuition about why they can do that. So are we clear on the scope of today, folks? Now, all of these things, if you are seeing my screen, you will notice, let me give you a walkthrough to the code that, and I'm trying my best to share it. I'll share the whole code in a Google Drive till our portal comes back up tomorrow. Till then, I'll put it on Google Drive and share the link on Slack. Is that fair, guys? Right. I'll do that. Just bear with me. And the course portal, when it comes up, we'll get more organized. Now, it's this code base, this directory, it is made up of two basic directories, notebooks and something called svlearn. You wonder what SV might stand for. Yes. So this is our library. All our libraries start with the word svlearn. This svlearn contains actual Python code, much more serious or longer Python code. For example, if you want to see how the universal approximator is done, it's not too much. It's just a couple of 100 lines of code, but you're welcome to read through this. And I invite you to read through this and make head and tail out of it. Is my screen visible and big enough for everyone in the audience? Yes. Yeah. So as you notice, so all of this code in the beginning will look rather strange. But today I'm going to walk through this code very, very slowly. Now, it doesn't mean that you'll understand everything in this code. It is just to give you a flavor of it. Now, all the code that is in the svlearn directory, consider it to be a stretch goal to understand it someday, not today. Are we together? Right? Because it takes some level of Python fluency and some familiarity with data science libraries. Even though I will explain it, you may or may not get it based on your background. So we'll go through some of that. But leaving this aside, the code that you find, and there's a bit of code here, the code that you find in the notebooks, you'll find a few notebooks. And just as a teaser, I pulled in something called semantic search, which I was actually teaching just this Sunday to the people who are taking the boot camp to give a practical flavor. It was a hello world for them, sort of. I brought it in so that you get some taste on where all of these things are leading. Today we'll start with simple ideas, and those ideas you'll get a taste of where it goes. So these things that you see, what I would suggest is we will go through the process of installing Jupyter Notebooks. It's a software. A lot of data science is done in, actually much of the data science people do these days. If they do it in Python, they do it in Jupyter Notebooks, and they do it in Visual Studio Code. So if you notice, this is Visual Studio Code, VS Code. It is a very popular IDE. It's also free. It's completely free. And I would invite you, I'll take you through the process of just installing it on your machine. Once you have installed it, and I will go over the setup a little bit. More of the setup, the teaching assistants will hold special sessions to walk everybody through setups. Are we together? Otherwise, the whole day today will just spend in the setups. So if you feel that this is all very strange, today try to follow the main ideas. Rest assured that our TAs will work with you as long as it takes to make sure that your laptops are properly set up to do all of this. And they are here in the audience, they're just muted. We would rather hear you speak. But there are 6 of them here. Now, and this is important, guys. We'll hold a session. We'll hold multiple sessions. They will announce it. Typically, it may be in the evenings, because I think evenings is a preferred time for Californians. Most Californians don't wake up in the morning. So watch out for those sessions to help you set up. If you can't make it to any one of those sessions, then what do? Request a TA to give you one-on-one time. But I would suggest don't all of you request special one-on-one times. Otherwise, poor souls will never get any sleep. So try to attend the common sessions. They'll patiently walk you through. Actually, one of the sessions I'll be giving, come to those sessions. Will help you set up the environment. Today, just enjoy the big ideas. Right? So with that there, I'm going to get to a very simple thing. I'll show you some bit of fun stuff. And again, let's move away. For those of you who are new to code, I'll just move away from this to something. Our first architecture. What is a neural architecture? What does AI really look like? Can you and I build our neural network of our own? Whenever we think of neural networks, or we think of big, large language models, our first instinct is that it sounds like a F-35 fighter jet, right? You and I can't build it unless we have a few billion lying around, right? And access to a few 100,000 engineers, talented engineers. That's your basic reaction. But it isn't like that, actually. Our field is based on very simple ideas, but repeated over and over and over again, scaled out. Are we together? So it's almost like once you get the idea, you notice that in the field, it's customary to just exploit that idea as much as possible, make it as big as possible within the constraints of the hardware, and to push the limits. As we talked about, one of the things we find and we don't quite understand is the same architecture, when you scale it up, it starts developing gradually new abilities, right? And it is able to solve a lot of problems with astonishing accuracy. Many problems that you would normally not be able to solve, you can do it with Great, great accuracy. Right? For example, I'll give an example just to give you an idea. There used to be a problem which was handwriting recognition, digit recognition. Because, of course, most people used to write on the envelope and then people had to parse what's written and digitize and so forth. So those you probably know that the postal system in the United States uses neural networks. That's why your letters don't get lost and they actually reach you earlier than you think. It's because once the letter goes into the mailbox, it is fully automated till it reaches the destination. The only human touch there is at the destination where another postman picks it up and delivers it to your house. So, so obviously it was of importance, central importance to have good handwriting recognition. So there's a data set called MNIST, or NIST. NIST, of course, you guys know, is a US body, National Institute for Standards and Technology. They set a lot of the important stuff in the country, like the rules and the standards and so forth. And they created a data set called the NIST, which with the modification became the MNIST. MNIST is was considered very, very hard a couple of decades ago, or very hard to, not long ago. For handwriting recognition, people tried the state-of-the-art methods. People used to get about 60%, 70% accuracy. At 60, 70% accuracy, it's not terribly usable. Right? Human handwriting comes in all sorts of shapes and sizes, ways people write. Just think, in how many ways have you seen the number 7 written? Right? Or how many ways have you written the letter, the digit 8, right? Or so forth. Any of those, or 4. And how often your 4s look suspiciously like mines. Right? So it was a tough problem, and there was a continual improvement. The community of AI has been progressing, and obviously there were a lot of algorithms that tried. There were support vector machines, which made a huge advancement on that. Finally came the deep neural networks. And in this course, because we have to pick and choose the curriculum, we have decided to principally focus on the deep neural networks because there's so much happening here in this space. So these deep neural networks, when they came about, they made a huge improvement to NNIST. Today, they not only, the computer vision systems, not only outdo humans, they outdo humans by a wide margin. They're far more accurate in reading handwriting than humans are. In fact, the error rate is I believe it's 99.9 some percent accuracy. And if you look at the cases where it could not tell, you look at that and you know that it would really stretch your imagination to believe that this was a number at all. It's just some squiggle mark labeled as a number. So in other words, the AI has reached near perfection. Right? You see this improvement in everything, right? In for example, text classification. It used to be a hard problem. Now algorithms routinely do 20, 30 years of history behind it. They do it with near perfection. They do it very, very well. So, but when you look at the ideas behind it, these are not necessarily, there are ideas that we'll learn about, but a lot of it is taking simple ideas and repeating it over and over and over again. Right? It's literally like that. Whenever I think of neural networks, sometimes, not exactly a good analogy, but for me, it always resonates. I think of fractals. You see, sometimes you see snowflake fractals and all of these images. You see repeated patterns. And you look at that, and quite often you see a little bit like that. Well, obviously, it is not fractal by any imagination. Well, there's some connection, but not that. So what I want to show you is a neural network is actually something very simple. It is made up of, like, to write it, first of all, I'll just create what it takes to build a neural network in terms of code. And then I'll show you how to use it. So when you look at it in terms of code, common, let's say, let's take something that classifies loss function, learning rate. Yeah, this is it. Rate. Well, I won't go over it, but let me show you one important part of a neural network. I said that you have to train a neural network. This word comes over and over again, and I'll come to it. So imagine there's a neural network. How do you train it from data? How do you teach it? That's a big thing. So what you do is you shuffle the data. Are we together? You shuffle and you take this data. So suppose you have to train it for predicting something. Let's say predicting the weather, or predicting a function, or predicting some number, or telling a cat from a dog, something like that. That's a prediction. In the world of AI, you call it a prediction. What is this? It's a cat. We predict that's a cat. Well, it's not really prediction, it's sort of identification, but we generally use the word prediction in this space. Or what's the temperature going to be at 2 hours from now? That's a prediction. Right? You're predicting a number. How do you train a machine to predict a number? What you do is you need data to teach it. Right? And so let me give you the basic idea, and then I'll draw it all out, guys. In a moment, I'll draw it all in boxes. But let's go over high level, and then we'll go deeper. What you do is you take lots of examples. So you say, this picture is labeled cat. Right? So what is the input? The pixels, isn't it? And what is the output? What is the output? The word cat, the label cat. Then I show a picture of a dog to the machine. That data is also a pair, picture and a label. You say picture is the input, label is the output. So you're giving it input and output. You're telling it the answer. The answer, the initial data set in which you say, look, this picture is a cat. This picture is a dog. Right? This picture is a house. Right? That is called the training data. The nature of training data in this particular example is you not only give it the input, but you tell it what it is. You tell it the answer. The answer, the word people use in this field is, it is the ground truth. That people use the word label, ground truth. These are interchangeable words. Right? Or in a very simple way, you can say, given this input, the correct answer is that, cat, dog, horse. Are we making sense? That's what it is. This is an example of something called classification, and we'll talk about all of those algorithms shortly. Classification says, which of the things is it? Is it a cat, dog, horse, for example? Right? 3 possible classes if you take. Yeah. That's that. So imagine that you have a 10,000 rows of data, training data. Now, remember, the quality of training data is you give it the input and you give it the answer, that you give it the ground truth. And what you do is you do it like this. You give it one input, you look at the output. Output would be, and here it gets interesting, it will say, I think it's 70% likely that it's cat, 20% likely it's a dog, and 10% likely that it's a horse. Right? So let us say that you know that it is a cat. The ground truth is that it's a cat. But the machine predicted at this moment, when it is still learning, that 70% may be a cat. So now the error is small, right? Because the certainty would have been 100% sure. You wanted to learn to be 100% sure that it's a cat when shown a cat. And you want that the probabilities of the horse and the dog should go down. Does that make sense, guys? Right? Maybe this merits a little bit of a drawing. Let's do that. So we know what we are doing. Um, I will give me so I'll put these ideas and then we'll see it all goes. So imagine that you have this machine that you want to train. This is your machine, right? You usually call it a network that you want to train, but it doesn't have to be a network. The same thing applies to other classes of AI algorithms, machine learning algorithms, like as basic as logistic. There are many things: logistic regression, decision trees, forest, gradient boosting, support vector machines, and huge amount of it. For paucity of time, we won't be doing that. So when I use the word network, quite often that thing can be generalized to other algorithms also. Just remember that. Right? So suppose I give it a picture of a cat, X. Now, in our terminology, we always use the word xi for input. So this is established in our field, input. If in a textbook you see xi, it means input, one input. Are we together? And yi, so when you give it xi and you know the answer that it should produce, the label, this is your label, ith label, this is your ith data input. Are we together? Inputs are always vectors. Right? Vectors means they are array of decimals, right? 2.13, 4.3, or whatever, 0.39, etc., etc. They are decimals, positive or negative. They are vectors. So that's something to know. Vectors. Inputs are always vectors. And output in this particular case is a label. When you produce a label, when the ground truth is a label and not a number, here the ground truth can be, so let me just make two boxes. When ground truth or label is a label such as cat, dog, etc., etc. Right? It's a label or a type. You say, in other words, it takes one of finite set of values, right? I.e., more formally, when y can take only values in, let's say, a set, let me just say set S. And if any of these gets too formal, let me know. Dog, horse. Let's stick with three animals. Right? Oh, or we can throw in our cows and ducks also because we used it last time. Why not? Cow, duck. So suppose it can take on values, only one of these five values, because you know that your input cannot be something else, right? So, you know, in exams, quite often you are given questions, and one of the multiple choices is none of the above, right? So let's not go into that. Right? So we'll just take it to be one of these five. The input, you're guaranteed to be one of the five. And you want to teach your machine to pick one from this. Are we together? When the target space, so this is called the target space. Like you think, so I'm deliberately rephrasing it in the different languages that people say. They say that there is a xi, there is a function xi. Remember, I told you last time that neural networks are, or all of AI, prediction machines, are just functions, fancy functions. So there is some function whose job is to produce a label, basically pick one of the values, right? When that is true, You call these algorithms classifiers. Classifiers. Are we together? And these things are the cat, dog, horses are these things are the elements are the classes. Classes. Right? Are we together? Now, those of you who are familiar with object-oriented programming know this. You define a cat to be one with two eyes, whiskers, and a nice tail, isn't it? And you give it a weight and so on and so forth, color, whatever. But then every object, every instance of the cat will can differ from each other. Just as in real life, all the cats, they are actually in subtle ways different from each other, right? Or sometimes not so subtle ways. So that is it. So you call them classes. It goes back to older, by the way, there is something quite interesting that I would like to mention as an aside. If you look at some of the oldest philosophical speculations in many civilizations, it was a realization that perhaps a lot of human knowledge is our ability to generalize from what we know and bucketize things into categories, into classes. When you have seen enough cows, you know what a cow is. You have in your mind a concept of a cow. Next time you see a completely different cow, you still call it a cow. Are we together? Right? So that is that's something to remember. Right? Now,
so Asif, the output is basically a scalar value.
The output is a label. Cat, dog, horse. But in reality, it's a two-stage process. The way classifiers typically work sometimes is many classifiers, not all of them. So that you can produce cat, dog, horse, etc., etc. Right? This function. But sometimes what people do, or some classifiers, they have an in-between sort of a stop along the way. They're actually made up of two stages. What they do is xi goes through a function, a probability function, pxi, that produces the probability of a cat, p dog, p horse, p cow, and finally p duck. It will produce probabilities. Right? And if you think that's very intuitive, right? If you look at something that you don't fully understand, this animal, if I showed you a zebra, for example, and you had to pick amongst these five, or a donkey, let's say, if I showed you a nice, cute donkey here, then what would be your reaction? Let's say, well, probability of it doesn't quite look like a horse, but probability of a horse is high, isn't it? Cow may be second best. Dog really pushing it. And cats and dogs probably close to zero. That's how you would think, isn't it? So think of machines are like that. They're never sure. They only speak in uncertainties. So now we have produced a probability. How do we emit out the label? Probabilities are numbers, right? They take on value. Probability takes on value from 0 to 1. Right? Probabilities take on values from 0 to 1. So all you have to do is pick the element with the highest probability, right? So you say label, where p label is max, is the argmax. Whichever maximizes the probability, right? Whichever has the highest probability. I won't write it in full math notation because common sense says it. You just pick so I'll pick another act, pick the highest. Are we together? You pick the highest. And therefore it becomes a classification engine. Now it turns out that this is how neural networks, it belongs to those classifiers that actually produces, the whole network can be thought as one big probability machine. Are we together? When you're trying to classify things, like identify cat, dog, horse, whatever, then you can think of the neural network as just one giant probability function.
So, can I think of label as a variable, a string variable, or a character variable?
Yeah, you can think of it as something like that. That's how it comes. So see, many things, right? For example, you sometimes think about it this way. You get data. It shows that for somebody with this income level, this purchase history, they had this credit card data. Probability, did this person default on the loan or not? Or credit card mortgage or credit card loan. So you get the answer in very discrete terms. One of the two events happened, isn't it? Either the person defaulted on the loan or did not default on the loan, right? But when you are predicting and you don't know, right? It's a person who has not defaulted, or maybe you don't know the answer. What can you say? You can be to a certain degree sure or believe that the person will default, and to a certain degree believe that the person will not default, isn't it? And the two will add up to one. So we ourselves would think in terms of probabilities. That's that. Now, this is classifiers. So this class of algorithms are called classifiers. To train them, what do we need? We need lots of, let's say, x1, and we know the answer, y1, x2, y2, x3, y3, all the way to xn, yn. You need a lot of data, paired data, input-output data, right? Are we together? For example, it could be x could be the picture, y could be the answer, the label. X could be the financial aspects of a customer, right? It could be a vector, for example, income and how many payments the user is making and so on with respect to the proportionate to the loan and so forth. And a y could be defaulted or not defaulted. But this machine, what this machine comes up with, so this is classifier, right? Now, do you notice that to train this machine, the trick is you ask it, how likely is it? Suppose you know that, and this is something interesting I'll mention. Suppose you know that the machine, this person did default. And your probability, your machine says, and what the machine says when you give it an input, let's say xi, what the machine says, you always make it wear a hat. Do you see? I put a big hat here. Let me make it even bolder. Guys, do you see that hat? Hat. Predictions wear a hat. What machines predict, wear a hat. It's a mathematical convention in our field. Right? So y is the ground truth. Y hat is the machine's prediction. Now, ideally, you would want to see that y hat I and y I should be identical, isn't it? But it's usually, there's a gap. For example, suppose it's a cat. Suppose a picture is a cat, right? It's a cat. So what should be the probability of cat is the ground truth. It should be 1. And you came up, your y hat, I, came out for this. So let me just say y I is this. So what is y hat? Let's say, pick a number. Let's say that you came out with, I'll take 2 possibilities. A possibility, you came out with 0.9, and B, you came out with 0.1. Now, which of the two guys is doing a better job, A or B? A. Now, how do you say it? A is closer to the right answer. Probability should have been 1 for cat, but you got 0.9. So now you may be tempted to say, okay, let's take the difference, right? But for reasons, for mathematical reasons that at this moment we won't go into in the first lecture, you don't do that. Right? What you look at, and it has to do with something called um, maximum likelihood estimator, and there's a bit of mathematical theory, but I'll try to condense all the theory into some very intuitive ideas. So I'll ask you this. Let's look at the degree to which you're surprised. If you know the answer, and the machine comes back and says 90% sure it's a cat, are you surprised? Not so much. But on the other hand, it comes back and says 10% that it's a cat. What? It means the machine isn't doing its job well. It needs to be taught better. Would you agree with that, guys? And so you realize that the amount of degree of surprise and and I'm using very intuitive language here. So the mathematicians amongst you, feel free to howl. Right? So degree of surprise is somehow reciprocal to the number, right? Now, suppose you want the degree of surprise to be, you realize that if it was 1, how much would your surprise be? 0. If it was 0, it says, no, it's not a cat at all. You're infinitely surprised. That's how you want. So you want your degree of surprise to go from 0 to infinity. You are looking at this number, a probability that the machine is producing, and now somehow let's think through and engineer a formula for surprise. Right? So the first thing you notice that as the number goes up, your surprise goes down. So what can I do to produce that? Maybe I can do 1 over p, 1 over y hat, right? The prediction. So now notice this quantity. If I do the reciprocal, when for A, I'm doing 10 over 9, isn't it? Which is approximately what? 1.1. And B, I am doing 10 over 0.1. And what is that? 10. So this begins to look good, right? If I kept the amount of surprise as a tentatively, as a possibility, and we are trying to invent the mathematics from first principles. People often say, oh, I'm scared of AI because it's full of math. Actually, it's full of very dead simple math. Yeah? And you can reinvent the whole math just by reasoning through it. So would you agree that this looks like a good idea? When probability is high, this number is low. When probability is low, we are hugely surprised. And 1 over probability seems to be doing pretty good.
Sorry to interrupt, but
Sure.
10 divided by 0.1 is not 10.
Oh, I'm sorry. 1 divided by. It is 1 divided by. And so it becomes, I apologize, it becomes 10 over 1, and so 10. Right? Now it is 10.
Yep.
Reciprocal.
Yep.
Thanks for pointing the typo. Right?
No problem.
So now that looks like a good idea, but you notice that when I'm not surprised at all, let me take a case C. It says 1.0. Probability of a cat is absolutely sure. I'm absolutely sure it's a cat. Then how much surprised should you be? Not at all, isn't it? So, well, it seems to be good, but C is still producing 1 over 1 that is equal to 1. But it seems to say that there is a little bit of surprise left. Not good. So then we are pretty close to it. How do you take something that goes from, so now it's just a simple observation. If some quantity goes from 1 to infinity, how do you make it go from 0 to infinity? What can you do to 1 as input that will produce 0? Think of some things that you can do to 1. If you subtract, then the trouble is you will start getting negative surprises. You cannot do 1 minus y hat, right?
Divided by a large number, you get a much smaller.
Go ahead.
You start cutting it down piece by piece until you get closer and closer to zero.
Yeah, it's actually simpler than that.
Exponential.
The opposite of exponential. What happens if you take the log of it?
It's log of.
What is the log of 1? 0. What's the log of infinity? It's still infinity. So this is a very simple mathematical argument. And so what are you saying? You're taking the log of 1 over yi, isn't it? Or predicted yi, right? Are we together? And indeed, that is all there is to it. For classifier, the loss function is log, and usually you take natural log yi. Now, this evaluates to this, right? Because this is equal to log 1 minus log yi hat. This goes to 0, and so you're left with this. And now, if you look at the total surprise, across all the data points that you gave, because you gave it 10,000 examples. So what you do is, so guys, get this thing. You go through the data, one complete step. Let's say in the beginning, you went through the entire data. When you have gone through an entire data, you would have accumulated the loss, the total loss or total surprises. People use the word loss, but in our intuitive language, total surprise or accumulated surprise would be log yi. Does that seem reasonable? Guys, have I said anything that's totally not dead obvious? If I'm going to show you 10,000 or 1,000 cats and dogs and horses, and each time you have a little bit of a surprise, what do you want to do? You want to train the machine in such a way that the total surprise that you get is very, very low.
Y hat.
Oh, absolutely right. Y hat. So guys, I do keep making little typos. Please do correct me as I go along. Thank you for that. Does it make sense, guys? Right? And that is literally the loss function for classifiers. There is more to it. There are regularization terms, etc. But for our first session, this will do. Make sense, guys? Right? This is it. Now, sometimes people average the loss. Like they say, let us divide the loss by. So depends upon who you're looking at. Sometimes loss is written as 1 over n, the total number of data elements. Suppose you have n data elements. I goes from 1 to m, sum over, and log y hat I, of course, with a negative sign. So you will hear the word negative log, and I just introduce you to a term that you'll see all over literature, negative log probability. Loss, quite a mouthful. You'll see it all over the literature and being talked about. You go to some article and it will say, oh, you know, I'm doing this and we took a negative log probability loss. From that, you can infer what are they trying to do. There's some classification going on likely in the background. That's the context. So wherever you're doing this, this term will pop up. So far, so good, guys? Now, any questions? I'll just pause here. Guys, if you didn't understand the concept, feel free to ask. I'm saying we are doing dead simple things. We are saying, here's a network. You give it, you know the answer. You show it some picture, let's say. And you say, what is it? Give me the probabilities of each of the animals. It has to be cat, dog, horse, cow, duck. So the machine will come chomp, 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 and it will come out with something. When the machine is not trained in the beginning, what will it do? Very much like kids. If they don't know what, they'll randomly throw out words, isn't it? So they'll pick a word. But then gradually, the idea is, and what you do is, with human beings, you say, for your kid, you would say, oh no, that's not a cat. Look, look, look. It has a tail. It has a wing, right? So it must be a duck or something like that. So you do a process of education. the process of educating networks is through something we'll talk about. We alluded to in the last lecture. It is gradient descent and back propagation. And people often use the word optimizer. What you do is the thing that gradually takes the machine through learning is the optimizer. Optimizer means it optimizes the output to align with the ground truth, the predictions with the ground truth. So the way it happens is at any given moment. Now the question is, in this one, I said all the data, N. You take all the data, right? Loss over all data. Total surprise over all data. This is called, when you accumulate surprise in one cycle, one step, through all the data. So what have you done? You have, let me put it there, batch. Batch, word, mini batch, and stochastic. You notice that the word gets more and more bigger, right? So when you take back once accumulate loss terms, loss, or if you want to think surprise over all data first before one step of learning. Means you learn from the total loss over all the data, total surprise over all the data. That kind of learning is called batch, right? Batch learning. And because learning takes place through gradient descent, these words are often suffixed with gradient descent. But for today, consider gradient descent as synonymous with learning step. Are we together? Gradient descent, a simple word, is learning step. So I can do one step of learning, and this word is important, guys. I introduce you to the concept. The big word that in the lab you will use, step. So one step of learning in batch is first run the machine through all the data, isn't it? Or rather, run all the data through the machine and accumulate your surprises. And once you've accumulated, that's your total loss. That's your batch loss, full loss. One step, and then you do one step of learning. How we do one step of learning, let's keep it for later. Now, mini batch we'll come to mini batch. Then there is something called stochastic gradient descent. It takes the opposite approach. It says, no, what if the batch size is gazillions of data instances? What it means is I have to run all this data through this machine, and then it's going to take one step of learning, right? We are not going to do that. Right? And indeed, there are sometimes situations, what happens is, given the hardware resources and constraint in the time it takes to train the machine, sometimes one journey through the data is all you get. Right? There's a word for that journey. It is called epoch. Epoch is one journey through the entire data set. Right? So we are getting introduced to the vocabulary here. Journey, a complete journey through the entire data set, training data set, is called an epoch. Are we together? Epoch.
Is epoch the same as stochastic or the opposite?
No. No, nothing. It's a different word. I'm saying a complete journey through the data. When the machine has seen every sample of the training data, once it is one epoch.
So it's the same as batch step and epoch.
Yeah. So now the question is, what is the relationship between epoch and step for the three modes of learning? That is what we will talk about now. Right? Surely there is a relationship, isn't it? So the relationship is, let me shrink it a little bit. Oh, touch on. Not able to shrink it. Okay, I will scroll down. So let's look at batch. A batch, we say, what every step you have to go through the whole data to accumulate the loss. So in batch learning or batch gradient descent is the technical term that people use, gradient descent. But can I just informally call batch learning? In batch learning, epoch is equal to step. Why? You just refuse to learn till you got all the loss accumulated from all the terms. Right? Now, the other extreme is stochastic gradient descent. Stochastic, quite a mouthful. Stochastic gradient descent What it says is the other extreme. I'm going to learn from, see, I get a loss from just one instance, isn't it? I just take one picture, feed it through it, I get some probabilities. It was a cat, and now let's see what's your probability that it's a cat, right? And then I can, by the way, in the loss function that I wrote for multi-class, there's some subtleties, a little bit more, but let's gloss over it. So I accumulate some degree of loss, right? Why can't I learn from that itself? Take one step of learning, right, by comparing it with the answer. So the intuitive picture is, guys, sometimes have you taken quizzes in which the moment you answer a question, you're allowed to see the answer right then and get feedback on the answer? That is stochastic quiz, if you want to learn stochastic learning, because you just saw the answer in a way. So that's what you do in stochastic learning. You pass one bit of data through the machine, you look at what probability it gives, answer it gives, y hat, compare it to y, you get your loss, and then you do gradient descent, right? You do a gradient descent step of learning, right? That is, so epoch there will contain how many steps now? Suppose there are, let's say, n data points for training. Let's say, imagine a number, let's say 10,000. So how many steps will an epoch have? 10,000 steps, right? It will have n times steps. N steps, isn't it? Roughly speaking, 10K steps in this particular example. Does it make sense, guys? This is the other extreme of learning. The next.
So it's always like get only one data point?
Come again?
It's like take always only one data point?
A stochastic gradient descent. If you take the stochastic gradient descent approach, you learn little by little. Every single data point you learn a little. Every little point you learn a little. Now, guys, what can be, I'll take the questions. What could be, first I'll pose the question to you guys. What could possibly be wrong with it?
Time it takes to go through 10,000 steps.
Yeah, see what happens is, yeah, that's a good point, Sidhu, that you brought up, and I think somebody here said slow. That is one practical problem, which is that every time you learn, actually learning is very expensive. Practicality is you need something called, we talked the word gradient. Gradient is a derivative of a function. Derivatives and propagating the derivatives back is far more expensive than computing the function forward. In other words, if it is a machine, if you compute fx, it's easy. Computing gradient of f is quite a bit more expensive. So what happens is that at every stage, from every data, you're learning, right? So there is a lot of computes going on. It does slow things down. The advantage, of course, the countervailing point is that you get to see progress rapidly. You're not waiting for a gazillion rows to go through, the whole data set to go through. You're literally seeing progress. And it opens the door to something called early stop. If you notice that the machine has learned enough, quite often you don't even run it through the whole data set. So you don't even do one epoch. You just sort of say, enough, right? You can stop early. And what you do is you look at how is the loss, the total loss, moving with steps. Because here, now your step size is very small, it's just one. If your loss has flattened out, do you think that there's much value in going on and on and on and on? You might not
No.
even be done with an epoch, right? This is it. On the other hand, if your curve is looking like this, and you are at this, let's say that you are at this data point, and you may have even run through two epochs, like gone through the data over and over again and let it learn. At this point, what would you say for the green line? Is it time to continue learning? Isn't it?
Yes.
Because for each step, the machine is still making progress, right? So it's very important then that when your machine learns, visualize, right? And I keep speaking about visualization, guys. Think about it like that. Our intellectual ability to reason may have evolved, let's say 100, 200, 300, 1,000 years ago, right? Let's be generous, 1,000,000 years ago. But our ability to see and grasp, we have inherited from fishes and even more primitive things. And they have a history of at least a few 100 million years. So if you think of those eyes as learning machines, which they are, it has genetically evolved into things that in the blink of an eye, just in a millisecond knows what's there, isn't it? Never underestimate or underutilize this asset. Wherever possible, visualize. Wherever there is confusion, I guarantee you, you are not spending enough time visualizing it. Guarantee you, whichever project. People will say, well, how do I visualize data in, my data is 50 dimension or 100 dimension, 1,000 dimensions. How do I visualize it? Oh gosh, remember, in how many dimensions can you and I visualize? Mine stops at 3, right? Beyond that, I'm stuck. So I did a lot of theoretical physics, and much of it, we realized that the world is in 4 dimensions, but we will use all sorts of tricks to sort of get an intuition. Beyond 4 dimensions, we would be lost. So we would just use mathematics and then talk to each other and say, as is obvious in 11 dimension. It wasn't, of course, obvious, but the math was obvious, right? So, but what can you do? What's the solution to this when you get data in high dimension?
You got to break it down into smaller pieces until you gain a understanding of some level.
Yes. So what you do is project it down in the most meaningful way down to a dimension that we can grasp, 1, 2, and 3. Let me make it quite obvious for you guys. Let's take human beings, right? How do we project human beings in 1 dimension? Think of some practical thing we do to project human beings down to 1 dimension. Height, exactly. And unfortunately, these days, weight. Right? So you just projected a human being down to 1 dimension. And yet you can tell from the height if you're talking about children, many things you can infer, isn't it? Because a lot of values like the age and other things contributed to that one thing. So height, therefore, is a good down projection. Right? But you can create synthetic, maybe you can create another axis that has more of height, less and some of weight and some other attributes mixed into it also. You can project down to one dimension. Can we project data down to 2 dimensions? Yes, you can. Right? You can likewise project it down to 3 dimension. Right? But now 2-dimension projection should be your norm. People forget that you can also do 1 dimension and get some extraction out of it. 3-dimension, remember one thing. 3-dimension you should do only if you can interact with the data. You can enter. See, 3 dimensions is a nuisance. A static image in 3 dimensions contributes almost no value. Every time, so there is a professor here at Stanford, Edward Tufte, who has written a lot about the display of quantitative information. And he says, so his absolute paradigm of how not to visualize data is a 3-dimensional pie chart, among other things. Why? Because the 3rd dimension contributes nothing except, and especially if you add nice color gradient and ray tracing and source of light to light it up, it just looks eye candy. But it actually is a distraction because the 3rd dimension is not contributing anything. So one of the things is information to ink ratio. So he doesn't even like pi. So you notice that in modern visualization, pie charts are disappearing. You can represent that information just as a bar chart. If you insist on a circle, you can still do it as a sort of a donut, break up a donut into parts. Okay. Also, like we can compare much more when they are vertical rather than when they are by area or by size or by angle. So that's that. So anyway, visualize, but in 3 dimensions, the beauty is 3 dimensions is very powerful, but make sure you can interact, you can zoom in, you can move the camera, you can rotate. Otherwise, 3 dimensions are no use. Don't get into the cutesy part of it.
So I think the one that I had was more epoch and more overfitting of the
Oh yes, very good point. May I request you to hold on to that for a little bit? I'll talk about the topic. In fact, you answered the question I was going to ask, but hold that thought in a moment. So guys, so stochastic is one, you learn from one data point. Your question.
Yeah, so in training, you could do multiple epochs. So for stochastic gradient descent, you always do just one.
No, you can do many. You should do many. So how many epochs should we do? Irrespective of whether it is batch, mini batch, or stochastic, you should look at the loss versus step graph and see when are you saturated, when are you flattening out, right? When are you flattening out? In fact, you have to be a little bit more careful. You sometimes freeze the model and you then apply the validation data, because the worst thing that can happen, and in fact, the point that you raised quite well is validation data. Let me use a different color. Could be going like this. Validation on a data that the machine has not seen. It may be going like, remember we said that there's an optimal degree of and you train it more and more and more, and then it begins to overfit the data. It's not that extreme, but it's sort of like this. It begins to go out, right? So you want to have early stopping. Just when you see that your validation errors on validation data set. What is validation data set, guys? The data set you never show the model. You hide it under the pillow.
In that case of the graph of the red graph, where would you stop?
You would stop here. Right? You would say enough. Right? You would say enough. That's early stopping. But again, guys, how many epochs you run, how many steps you run, should be informed by how loss is doing. Right? Are you gaining anything from running more steps? That is the measure. It's a very practical measure. Am I gaining anything by burning more compute cycles? Right? These days, especially when you're paying for cycles in the cloud, it's a common sense measure. Right? Now it turns out stochastic gradient descent is not just computationally heavy, it has actually a flaw, a subtle flaw that sort of, not really a flaw, but it's sort of part of the baggage that comes with it. See, when you learn from a data instance, the presumption is that that instance is completely correct, right? But what if that is not true? For example, if it is not classification, but predicting the number, let's say temperature tomorrow, right? Or something like that. So then what happens? It's a number. You have measurement errors, right? And with classification also, well, between horses and cows, right? There may be uncertainty in the picture, right? And so on and so forth. So anyway, the reality is when you learn from a data point, you do not acknowledge the fact that the data point itself has built-in errors. This is especially true with numbers.
So are we saying that the error is being averaged out, or like the rate
No,
of the
Gopal,
error
when you
is
learn
will be
from
less
only
than
one
your
data,
batch?
when you learn from only every data
Yeah.
point, what happens is it is pushing the information part of that. Like let's say that the temperature really was 100 degrees. But in your data, your Y, your temperature is saying 102 degrees. So what is it? You're telling that under these conditions, the temperature is 102. And therefore, if you predicted 98, right, you're way off. Whereas in reality, you're only slightly off. Right. So the point I'm making is every data point inherently will have some good information, something right, and potentially something wrong, some error built into it.
So in that case, is batch better to get less?
No, we're coming to that. So hold that part. I'm coming to that. So you realize, you learn, hold on, guys, all of you, please hold on. When you learn from one instance of data, therefore, I'm saying that it both informs and misinforms you, partly, isn't it? Hopefully, it informs you more than it misinforms you. So what will happen? You will sort of go in the right direction, but veer slightly off track, right? Let's say that under the same circumstances, there was another, or more or less the same circumstances of input, there was another data point somewhere where the temperature measured was 96, way under measured, right? Now that also is very close to 100. There's a lot of information there, but it's veering you slightly off track. So what happens is when you'll see this in a certain world, it will zigzag its way towards the right answer, to the perfect answer. In stochastic gradient descent, you zigzag your way there, right? Because every piece of data is partly taking you in the right direction, partly veering you off. Slightly you're getting veered off, right? Okay, questions. Madhu, go ahead.
There's a question in the chat. I'm going to just read it real quick. How would a learning rate scheduler impact the loss?
Okay. No, we are not. We haven't gone down. I've not even introduced the concept of learning rate scheduler. I've not introduced the concept of learning rate itself. So we'll hold that thought for another lecture. Today, let's stick with the basics. Those topics are coming, but let's keep it to simple ideas today. Go ahead.
So when you mentioned the loss equation that you brought from above, is that like the core equation when it comes to calculating the loss?
Yes, in fact, that's the celebrated cross entropy loss, right? Or it is the negative log probability loss. So all of these are close cousins. They're all the same thing, more or less.
Because they all know type of loss calculation.
Yes, that is right. So if you have there's a particular variant of this when you do only binary classification, cat or dog. It's often also called cross entropy loss, and negative log probability loss is the more generalization we have many times. You have a hand.
How is the finding the log minimum, like in the first lecture we have from the
Yeah. So how do you find it? At some point, right? See, theoretically, that's a very good question, and that's the whole question of gradient descent. That's the whole topic of next lecture. Hold that. But I'll give you a preview of it. See, your gradient will vanish. Take this. Or nearly vanish. Let's put it this way. Look at this. When you reach the minima valley, what do you have? It's flat. Flat means there is no gradient. That's it. Gradient vanishes. Now, loss gradient will vanish at the bottom of the hill.
How does that correlate with this graph?
Oh, the x-axis here is step. It has nothing to do with that. Right? That has nothing to do. Here it flattens. So here the only correlation is, if you notice that loss, here it's a loss with respect to step has flattened, but this is not the gradient we look at. Right? This is a practical gradient. We say, okay, now is the time to step. We have asymptote. We have an asymptote. Right?
So when we stop at that static process,
Yeah.
somewhere in the middle,
Yeah.
where we are feeling that okay, it's not yielding the results.
Irrespective of whether you're using stochastic, batch, whatever.
No,
That's a good point
in the
to
case,
start.
yeah. So can we take this learning
Yeah.
and fuse it with batch? I want to go to batch.
No. You don't change party loyalties midstream. Right? Yeah. Right. So, all right. So now, so what happens is we realize that batch gradient descent has a problem. You have to wait a very long time to run just one step, because a one step is a whole epoch. And God forbid, these days, the data set sizes are 100 billion instances and whatnot. It's not practical to take one learning step on such a big step. On the other hand, stochastic, you keep veering off, and computationally it's expensive. Right? But you get there, but you never hit the answer, because even you will just keep beating around the bush. But you will stop when you notice that your loss is just oscillating. Are we together? It's just oscillating. We'll see it in the lab just now, shortly. So there's a Goldilocks region in between. The Goldilocks region in between, or the middle path, is what? What could it be? So you pick a size. It's like when you go to the river, you don't take the whole river home. You take a bucket of water home, right? A batch of water home, a bit of water home, right? So that's what we do. Or when you go to a tree laden with fruits, you take a basket of fruits home. Go ahead.
When it comes, let's say there's a full size of 100, and then all data. So-
All data.
And then you need to separate that into a training and then validation or maybe test data.
Yeah.
What would be like a good ratio?
Oh, that is a very good question. So your question is a little bit off topic, but how do I split the data? Because if data is only 100, it's very precious. How do I survive? See, it's hard to tell. It depends on the domain. It depends on the problem. A 70-30 rule is a good rule to have. Some people stick with 80-20, right? And 70-20, 80-20, have your pick. When data is plentiful, then 90-10, right? Or 50-50. See, it depends on the context, right? But when you have just 100 data points, then 70-30 split, right? Or 80-20 split is pretty good. And then within that training, that full, you keep the test data away, you're left with 80 items. Within the 80 items, you do a cross-validation. So there's things like k-fold and all of that. There's a whole bit of machine learning thing behind it. But let's stick to the big ideas. So mini batch.
We have
Yeah.
one question. I think it's relevant to the topic. What makes the network learn? Does it store patterns?
We'll come to it shortly. It is right. We'll learn to it. See, there is a magical way to teach it to make less mistakes, less loss. So how do you teach it to make less loss is the mathematics and the whole topic for next time. Right, let's hold on to that.
Right. One quick question.
Yeah.
Between like a batch and the stochastic. You said that okay, stochastic is like a computational heavy.
Yes.
It takes a long time. But even batch is also like with gazillions of data, the same computation problem.
No, but remember, so very good question that you're asking. That why is batch not as computationally heavy as stochastic? Remember, if you run through one epoch in batch, how many learning events took place? One. Because you accumulated the loss and then you learn. In stochastic, how many learning events took place?
Every time
every single time.
Number of steps.
Right. So let's say that the mini batch size, the word is mini batch. Mini batch is a word. That's a formal word. Let's say that the mini batch, you usually write it with a little n. Let's take the size to be, let's say 32. Right? I'll take a size 32. Now what happens is you have a basket. Imagine your data to be the tree of fruits. Every time you go, you bring back a basket of data. And you accumulate the loss over the entire amount. I goes from 1 to n, little n. Are we together, guys? You accumulate the loss over your whatever your loss function is. And I did for classification, of course, I did that. I'll show you for regression also. Let's say negative log yi, right? You did that. And for the given class, let me throw that also in. There's actually a double summation involved here. We're ignoring, skipping some of that. So you have a loss like this, and you do a learning step. So how many steps are there per epoch? It is n divided by n, number of steps per epoch, Would you agree that this would be capital N over little n? Does it make sense, right? So if I have 10,000 data points and every time I go and get 100, how many times will I have to go? 100 times. So 100 learning events will take place. Mini batch. So generally, we believe that your mini batch should be your default. Now, when you deal with the libraries that you are going to deal with in code, you will notice a little bit of an abuse of notation. A lot of functions will ask you for batch size. Right? More strictly speaking, batch size is the whole data size. No, they are actually asking for mini batch size. What do you want to keep your mini batch size to be? Right? So remember, when they use the word batch as an argument in the libraries, they mean mini batch. Right? And mini batch gradient descent, a mini batch learning should be the default behavior, because it's the Goldilocks region between two extremes, isn't it?
That's a quick question. Sorry.
Go ahead.
So is there any science behind the batch size, or is that a random number that?
No, it is not a random number. In fact, you just encountered today something, a magical beast in the forest, in this forest, hyper parameter. So it is something that you don't know, and the network cannot on its own learn. So what you do is you try out different batch sizes to see which gives you the best result. Right? Hyperparameters are things that are frankly not used to be considered non-learnable. In a simplified version, think that you need to try it out, different batch sizes, and see what works. People take powers of 2, like 2 to the power k, typically as batch size. No particular reason you should take it, but it's a common practice to take powers of 2, 4, 8, 16. The other aspect to remember is it also depends on your hardware. In our world, there are people, there's a whole spectrum of hardware. If you're sitting on a laptop which doesn't even have a GPU in it, and you're using the integrated GPU, let's say the Intel integrated GPU, then you realize that computations are going to be very slow. You would rather use small batch sizes, right? Or you can play around with that. On the other hand, if you're sitting on a H100 or H200, well, good for you. You can take rather large batch size, especially at inference time. But at training time, actually, 2 smaller batch size and 2 bigger batch size, both of them can be counterproductive for the same reasons that we talked about. Yeah. So it is pretty common to take 4, 8, 16, 32, even 64 sometimes for training. But training, you don't take very big batch size. At inference time, when the model is fully trained, often you try to send up, because at that moment, the batch size is no more a hyperparameter of training. Training is over. Model is done learning, is frozen. At that time, what your batch size is completely depends upon what the hardware capacity is. Right? So, for example, you would notice that if you look at that, those of you who are playing with LLMs and fine-tuning it, you will often see that the training batch size is different from inference batch size. Inference batch size is often, especially if you have the luxury of a H100 or something like 128 data points that you can just shoot through that 128 inferences or predictions at a time. But when you're training it, you use a much more modest number, like 16, 8, 16, 32, that sort of thing. So hopefully that answers the question. So guys, this is the difference between batch, mini batch, etc. Now,
I have a question, Asif.
Yeah, go ahead.
There's a concept, and I'm trying to answer the question if the concept exists or the right terminology. So when initially you start training, say you have 1 million data points available to you. When you initially start your training, you may start with just 100,000 or 10,000 or what have you. So it's a smaller to start your training off. And then do you go to the full million that's available to you? And is there a different state or terminology from starting small to large? Or do you always do all of your training on the fully available data?
See, so the practical reality is when you have an idea, most likely you'll find yourself sitting upon a chair on your desk. And in front of your desk will be a hardware with limited resources. It will be, right? If you're lucky, it will be a nice Linux with a 4090, right? Or if you're one of those people who likes to buy commercial operating systems, you might be sitting on a Mac or a Windows or something like that. All of those have, like, to different degrees, they all have limited resources. If you have a 4090, you have more. So by necessity, when you're just having an idea, you will probably take a small bit of data, let's say 100, like 10,000 rows or something, split it up, try to train it and see what happens. If you notice that you train with 10,000 data and then you validate, you try, okay, what's the final loss? And then I try it with 20,000 data points, and you realize that 20,000 did make an improvement over 10,000. Then you know it's time to put in a request for bigger hardware. Move your workload to the server in your office, your data center, or the cloud. These days it's the cloud. That's when you want to obviously spin up something in the cloud with big guns and shoot bigger data set sizes. But in general, see, two aspects are there. There are situations where you need all the data to train, split, and test, and so forth. But just because you have big data doesn't mean you have to use big data. You should always experiment small. See, guys, this is literally what it is, common sense thing. And this is something actually escapes. People will have all sorts of articles and opinions on how it should be, but it comes down to literal common sense. Suppose I have one loss function. Let me take this. I have a loss function going like this. And this is for a data set size n is equal to, let's say, 1,000. Are we together? And then, because I know it may not be enough data, how would I know how much data is enough? You don't know. So what do you do next? You then go and try out another data set. You again take a random sampling. So guys, an important word. So there are certain statistical considerations. Yeah. You have to make sure that when you do this sort of A/B testing, there should be IID, independent, right, and identically distributed data. Means both the samples that you're training from, they should show the same distribution. Because if there is if the probability distribution is not respected, if you then the second data set becomes out of distribution to the first. You basically are at that moment, right? You have no idea. Nothing, no hypothesis you build is believable at that moment, right? But assuming that you still pick up IIDs, right, and a representative data set, but this time around, one of two things can happen. You can have a situation like this. Green, right? And we are talking about case A, and we are doing n is equal to 2k, 2000, or it could be, let's take this, this. It could be this situation. This too is case B, n is equal to 2000. So now tell me guys, in case, no, sorry, the other way around, I should not have made this picture so good. Guys, hang on, wait it out. Let me make it. This is, look at this, let me just call it case A, and green should have been much better than this actually. And this, my y-axis should be way below. I tend to be very careless or make sloppy mistakes when I'm talking. So let's say that case A, A is case A, and is no case. The purple line is case. Let me give it a name. Case P, the baseline case. And you have a case in which you took 2000 lines. It is this, and you have another case when you took this and the loss went like this for n is equal to 2000. Case B. So case A was with case P, the initial baseline case was, or let me just make it baseline, 1000 points. You got that loss function. You saturated at, they all saturate, isn't it? Loss is not going down anymore. Now, if you encounter case A, what is it telling you? Going from 1000 data points to 2000 data points in training, what is case A trying to tell you?
It's telling you that the function is given an equivalent result regardless of the size of your training data.
That's right. The machine has learned what it could. Throwing more data is not going to help you anymore, right? On the other hand, what is case B trying to tell you? Look at the loss. You have a significantly better model in case B. Much lower loss, isn't it? Asymptotic loss. So what is case B trying to tell you? Better data set. So you better go and now do one more. What would be a good color? Let me take this color. So it is encouraging you to go and do this, isn't it? Let's say this is n is equal to 10k, right? Or something like that. Case B, if it is true, is encouraging you to do the yellow operation, the yellow experiment. Isn't it, guys? So remember, guys, this field is often called data science. Science is about experiments. Instead of having opinions, you can have a hunch, you can have a gut feeling. Experiment. Experiments are cheap. Quick experiments can. Somebody actually do an experiment. A friend of mine used to say, a good laugh is worth 1,000 syllogisms, right? In the same way, I would say, for a scientist, a good experiment is worth 1,000 arguments, opinions. Do an experiment, see what it is. You're done.
It's a great line you said, sir. I love it. Science is about experiments. You go take more data and more data and more data unless you just flat lines, right?
Exactly.
As before you move forward, if you can hover back to the graph. I know this sounds silly, but can you make the purple case B as case baseline so that way it doesn't contradict with the green case B?
Oh my goodness, yes. I told you guys that you'll have to keep correcting me. I am the very, very error prone.
And the blue one you can remove, the blue and B and the green and the blue are the same.
Green?
And the blue.
No.
2000 and 2000.
No, I'm saying that either case A is true or case B is true.
Oh, okay.
So when you double the data set, one of these two things will be true, right? Either it's not learning anymore, then why burn compute cycles? The machine is telling you that I'm done learning, right? On the other hand, if it is case B, it's trying to tell you that, hey, look, you improved. Like, see, guys, so let's make a corresponding plot in a different way.
So you're saying it's either case A or case B.
Yeah, look at this, guys. If I plot asymptotic loss, final loss, I'll use the word final loss, but it is the asymptotic loss, the fully trained loss, which you take. If at data set size and the size of data, size of training data, what happens? If, let's say that the purple line had a final loss here, right? What do? You keep on increasing. You keep on increasing the data set size till this itself flattens out. Right? Look, if you look at it along a different axis, isn't it? So you just keep checking your final loss against the data set size and you're done. It's common. Like usually, guys, when you do experiment, use simple reasoning and you won't miss. You won't miss your path.
I'm curious, in your experience, have you ever had it flatline out and then after a short period of time start to reduce loss again? So it looks like it stopped learning, but then it starts learning again.
Yes, all the time. These things happen. In fact, if you went to the playground, in the TensorFlow playground, did I introduce you guys to the TensorFlow playground last time? Did, right?
Yeah, so I've shared the link in the chat, Asif.
And we can do that again. So you will notice that even for simple situations, it will see what happens is that the machine gets locked into a local minima. Remember, we saw the loss landscape of these machines, right? Do you guys remember that visualization, the loss landscape? Let's go back and let a recollection here. It will take a moment and then we'll take a break. We need to get into the code now after that. I'll finish one more topic. Yeah, we are doing a lot more theory in the beginning because we are just setting up the enough theory to make sense of what the lab says. So look at this, guys. If you look at this, do you realize that if you start somewhere high up, this is the loss landscape, loss function in an abstract space. It's a parameter space with a hypothesis. Every point in this figure is a hypothesis, is a state of your model, right? Is a set of values for your parameters, your weights and biases. When you do gradient descent, do you realize, if you look at it, how many local minimas there are in which you can get trapped, right? In particular, look at these dangerous ones. So what happens is you do get trapped there, but with luck, you bounce out of it after some time. So loss flattens, and then again, you have a dip in the loss. Right? You're on your merry way back to the minimum. It happens all the time. So this field is filled with lots of gotchas, guys, lots of things that you learn through hard experience.
Hey, Asif, a very fundamental question. So I thought in gradient descent, if it goes to local minima, it can't get out of there. But you're saying there are ways in which it can get it out of there till it finds the global minimum?
Yes, of course. And in fact, that's why I'm keeping gradient descent as a whole topic. So I'll give you a physical intuition, and that's all there is to it. It's a very physics-motivated argument. See, if a ball is rolling down the hill and a ball has a mass, do you think it will necessarily get trapped in every local minima or the first local minima and be stuck there? May not, right? If it has enough momentum, it will go into the minima and bounce out, right? What happens to your car when it is going on the highway and you come across a lovely pothole? It doesn't immediately stop there and get stuck. It just bounces through it and out of it. You just went through a local minima and came out of it. Maybe with a broken axle, but you came out of it. Isn't it? So that's it. Literally, you bring the argument of momentum. You give the gradient descent, you augment it with enough momentum, mass to the journey. That's it. Does that answer you?
Yes, it does. Thank you so much, Asif.
Sure. And we'll see all of this, guys. This field is enormously fascinating and built out of simple ideas, but beautiful ideas. We will go through all of that, all in due course of time. So, guys, coming back to where we were, I have only one more thing to tell. Now, you're all intimately familiar with what a loss is. And every time you compute a loss, you do a bit of learning. How we do the bit of learning, let's keep it for next time. But the magic mantra is gradient descent. Okay? Somehow you descend down the loss landscape. We'll come to it. Hold that thought in your mind. And now let's recap what we have learned. We have learned that classifiers are things, that target space is a label. Neural networks are nothing but giant functions, big functions. All neural architectures ultimately are functions, right? Except that these functions are not something you and I can imagine. It is amazing, amazing. But we'll be amazed in small ways today when we do the law. We came across a concept, very intuitive concept of surprise. And we realized that a good way is to take the negative log of probability. Right? We went through an intuitive argument to do that. Then we said that you could learn from one element at a time of data, item at a time of data, or you could learn from all of the data in one go and then repeat, or you could do in mini batches. Mini batches represent the Goldilocks region between the two, both of which are extremes. A complete one step of learning, one step of gradient descent is a step of learning. Epoch is one journey through the data. Are we together? And then we had some questions about when to stop, how to stop, and so forth. Now, there's one more class of algorithms, which also is obvious. I'll just talk about it and explain the loss function. And those are the only two loss functions we will need in our course. There's another kind of function which doesn't produce probability. So imagine another neural network. Input goes in, xi goes in. It just produces a number, yi hat. Right? It belongs to, let us say, in simple situation, just a number, a scalar. Right? A number. In reality, it could be a vector also, but let's keep it simple. For example, if you are predicting the wind, then you have to predict the direction of the wind also. Then it becomes a vector, right? So 2-dimensional, 3-dimensional, and so forth. You have to say 6 miles an hour, south-southwest, or something like that, right? I think the weather people must be having fun using that language. So then, when that happens, how do you measure the loss? How do you measure the mistake? See, the reality is itself a number. Let's say is the temperature. Let's take temperature, right? Or let's take a very intuitive example. Think of an entrepreneur who is trying to sell ice cream on the beach, right? Now, for this young entrepreneur, he has opened a little shack, right, on the beach, and now she's trying to figure out how much ice cream any morning to go and get from the wholesaler. Ice cream is a perishable good. You go and buy too much ice cream, what's going to happen to it? It's going to go bad. You won't have enough children on the beach, it won't sell. You lose money. If you buy too little ice cream, what's going to happen? She'll have an unenviable joy of sitting there and watching the other ice cream shop get all the customers. Right? So you need to figure out the optimal amount of ice cream to get. So what is your prediction target variable? How much ice cream? Isn't it? How much? How many pounds, let's say pounds of ice cream to get from the wholesaler, isn't it? Now, let's say that input could be multiple things. For example, it could be the temperature. Warm days attract kids and parents. It could be day of the week or holiday or not, right? Because who takes kids to the beach? Parents. And if they're tied down to work, they won't go. Day of week or holiday or not. Windy. If there are big surfs in the water, big waves, parents will keep the kids away, and many other considerations. Right? So let's say that all of these make your input vector is made up of these variables, and y is how much ice cream you're going to. Now the question is, how do you create a sense of loss? You would agree that if you in reality, let's say yi on that particular day, 100 pounds of ice cream actually sold, but your machine predicted that you would sell 80 pounds of ice cream. You made a mistake, isn't it? It made a mistake. What is the degree of the mistake? Yi minus yi hat, isn't it? So now you could say, hey, let's add up all these mistakes. Does that make sense? What could go wrong? If I add up all of these mistakes to get the total loss, is that fine? That's all right. What could go wrong? No, you hit it, because someday there would be some yj which could be 120 pounds, which was also wrong, right? And what will so this error, this is the epsilon I error could be positive or negative. It may undershoot or overshoot. And what happens when you add up all of these errors? They can cancel each other out. You don't want to you don't want them to cancel each other out. So you're looking at the magnitude of the error, not its value. So there are two ways you can do it, multiple ways you can do it, but one way is that you can do yi minus yi hat. You take absolute value and then you add it. Now we are in better shape, isn't it? This looks right. So people do that. It's the mean absolute error. In certain circumstances, it's a valid average. However, much more common is to use this thing. You can just square the errors. When you square numbers, they all become positive, isn't it? It has the advantage that bigger errors are bigger penalties. They're quadratic penalties, isn't it? And in fact, there is who discovered, by the way, this loss function. Can somebody guess when was it discovered? Well, I have a student from the past, so yes, right. I thought you would say right a few months before ChatGPT came out. No, I'm kidding. So yes, it is true, and it was discovered and in the 1700s. By whom? By Gauss. In fact, Gauss used this to make the predictions that became the famous paper when he predicted the position of the heavenly body in 1793. Later on, Legendre wrote, the great mathematician Legendre, literally wrote a paper whose name, if you look at this, is Method of Least Squares. This is it, right? These are the squares of errors. And what is the best solution when the loss is minimum, least loss? Method of least squares. 1805. That's when. And these algorithms which predict a number are called regressors. They are regressors, or people often say regression algorithms, right? Are we making sense? So that is all the theory we'll do today, guys, because we have to do some lab, and it's important that we do lab. We spend more time on theory than I had anticipated because I could see a lot of questions coming in. But guys, I want to make sure that this foundational theory is crystal clear. Do we know what's the purpose of loss? Is just how wrong you are in a very intuitive sense. There is more to it. Now you may say, oh, no, wait a minute. What about regularization? What about this? What about that? Well, let's keep it for another day. In simple terms, loss is how wrong you are. Go ahead.
Just a basic question on this step versus the stochastic. If computational power is not an issue, would the outcome of both of these be same in terms of the accuracy of the model?
See, what you literally see it in the lab. What happens is that stochastic never hits the minima as well as mini batch does, because it keeps beating around the bush. Every point takes it a little bit, veers it off the correct answer. It always does that. So it never stabilizes in some sense. So, all right, guys. So with that, I will take just a 5-minute break, and then let's come back. Today will be a longer session, guys. I apologize, but we need to do an hour of lab. This theory was necessary to get you started, right? To give you any perspective. In a traditional machine learning course, everything that I have explained to you in a simplified form is the context of multiple sessions. But I try to simplify it all down because the world is moving so fast and there are so many things we have to learn in 12 weeks that this is all we could do. But with this much theory is all we need to get started with lab and have it make sense. So guys, by my clock, my clock is saying 9:06. We'll meet at 10 past 9, which seems about 5 minutes.
Yeah, Asif, if you want to pause the recording.
No, I don't think I can, because streaming you can either stop, or if I stop it, the whole lecture will stop. I can post process and cut it out later.
Okay.
Yeah.
Yeah, I was gonna ask, do you want to cover this in the next session, because it's already midnight for some of the folks in East Coast.
Yeah, it's 9 o'clock already, sir. And we need to think about our session length.
Yeah, I'm concerned about you as well.
Okay. All right. How about giving me half an hour or not even that?
I'm fine with that.
Yes,
I just want to make sure everybody's okay with it.
Or post the lab and go over in a common session as an option.
Yeah, so some people are already dropping, so yeah. But it's okay, sir. If you can wrap it up in next 20 minutes, that would be okay.
Yeah, we'll wrap it up in the next 20 minutes.
Yeah.
Okay.
Easy. I just want to just button it up, make all of this very real for you.
Okay. Yeah, we'll take 5-minute break and come back. Yeah.
3 minutes are left.
All right.
Madhu, I have to drop. This is awesome, Asif. Thank you so much. But I have to drop. Thank you so much, Madhu. I will be in touch with you. Thanks.
No problem. Thanks for joining.
Isn't this lost landscape hauntingly beautiful?
I was actually saying I was doing pretty. Did you get to create that?
No, not me. There's a research. The guys who wrote this paper, they created a website, and now they have made it into art. They sell it.
I'll see you today, or tomorrow.
Oh, you too are.
Yeah, because I work on this time as well. I'm gonna get
short. All right.
Yeah, just make sure that the lab is on the Slack channel and you can review it.
Yeah, just give me 20 minutes, guys, to get. Yeah, okay. We are 2 minutes away.
That's cool.
Kate, are you recording it?
Yes, we are on that.
Okay.
Yeah.
Asif, you may want to take a couple minutes break.
He's gone much longer before.
Hashtag Energizer Bunny.
All right, folks, we get started now. It's we're on time. What I will do is I'm showing you now the main learning loop. When we say machine learning, when it comes to neural networks, this is a function like this is the main loop. Now, you don't need to know too much about Python, but I want you to appreciate that what is it? We are running through epochs, and we are running through in this line 157. Do you realize that we determine how many epochs will run through in this code, in this very simple code? We may have decided that the number of epochs is 10. Like, for example, here you notice I've set default epochs to 10 for this simple neural. For those many epochs, you do this. You take data. When you say for I data, what you're getting is you're getting mini batches of data. There's a lot that's happening that you don't need to worry about at this moment, but this is the basic structure. This line computes the loss, this particular line of code. Now, guys, I'm quickly going over it. You don't need to understand this yet. It's too early to understand it. You will understand it soon in a couple of sessions.
So, Asif, quick question, sorry, on this one. Is this a loss for a classifier, or is this a loss for the more generic one where you said can have any arbitrary value?
This kind of a loss, this loop, the only difference between a classifier and a regressor is what loss function you use. So remember, look at it. The difference between a classifier, like here, regressor has a sum squared loss, right? A mean squared loss, right? You square the losses. Whereas for a classifier, you take the negative log likelihood, isn't it? Look at this. So, but the basic architecture of learning remains exactly the same. Just the loss function changes. So this particular loop that you're seeing, this will be at some sense, this is the learning loop of machine learning. Right? This part, loss backward and optimizer step, this is the gradient descent step. There's something mysterious called loss backward, and associated it is the concept of back propagation. It's something unique to neural networks. We'll talk about that in subsequent, but ignore that. But look at the succinctness from line 170 to 173 is machine learning. What do? You put in data inputs. What do you get? Outputs. For a mini batch, suppose you send 10, mini batch is size 10, you send 10 inputs, you will get 10 predictions. Outputs are the predictions. Now, out of the predictions, you can compare it to the label to compute the loss, whether sum squared or cross loss. You can compute the loss. Once you have the loss, then the next two steps, 172, 173, learns from the loss. Is the learning step. You see the word step in line 173? It's the learning step. That's all. And this is it, guys. At heart, inside this double for loop is sitting this core 4 lines of learning. That's how neural networks work. That is it.
Would it be fair to say that you're describing a car and you're saying, okay, a car needs wheels, it needs a chassis, it needs an engine. You're describing all the parts. You've yet to explain how an engine works, but we need an engine and it does things, but this is the vehicle that allows the neural engine to work.
No, I'm saying that in a car has many things. I'm giving you the main engine. This is the engine. This literally is the main learning loop. Those 4 lines of code is the heart of learning in neural networks.
Hey, also, but in this code, when we get the Jupyter file, we will have the function backward, we will have the loss function, the optimizer step, all that we will have, right? That we can look at and hopefully try to make sense of.
Yes, you have everything. And that's why you don't write this code from scratch. You use industrial strength libraries like PyTorch. We will be using PyTorch and it gives you all these functions.
But the key thing I was trying to articulate is we actually haven't learned how does it actually learn? How does it store data? What's inside the innards? We're talking about the things around it yet, so we understand the bigger picture, but the innards have yet to be explained.
Yes. So
okay.
Learning, I haven't, but let's keep some mysteries for another day. That is it, because it is I want to explain it clearly in 2-3 hours so that we hold it in our minds forever.
Just a second. Is it Felix who is asking this question? Felix?
No,
this is yeah. But anyway, he's asking about the mathematical equations behind this. Is that correct?
No, well, there are 2 of us that spoke. This is Sarah right now.
Oh, okay.
And so just so everyone's aware, I'm transgender, so you're hearing a male voice, but identifies females, hence Sarah. So it's a little bit confusing just for vocals. But I'm just trying to, because I'm understanding the bigger picture and waiting in anticipation for when would the mysteries get resolved later on in the course.
Yeah, so like for all the mathematical background for these minute things, like Asif will go in detail in other classes for sure. So right now it's a very, very superficial things we are learning, and it's not possible to explain every single thing in one session, but it's very interesting, topic. And Asif sir, we can answer these questions in another like one-to-one session if somebody has that.
Yeah, right? The entire lecture is devoted to that. In fact, the very next lecture is devoted to this.
Yeah.
So we will cover, but I understand why you would want to know. I'm pretty much creating a suspense. It's like the TV shows, right? At the end, there is a big suspense. The main thing is not explained. So, well, here we go. I just created a nice TV show, 1 episode of it. But let's look at this.
What was the backwards?
Backward is some mysterious thing called back propagation. We'll learn about that. Right? Okay, guys. So now to the actual lab. Look at this lab. I created literally a feed-forward network from scratch, completely from scratch. This is made up of very few lines of code when you actually look at it. Right? You'll be surprised how simple this thing is. Literally this. Do you see this 4 layers? Actually 3 real layers. It has just 3 layers of neural network. Right? It is exactly what you were playing around with in your TensorFlow playground last time. Right? You remember that? So this is it. And look at the loss. As I go epoch by epoch, so I'm jumping some epochs, what do you notice? Loss drastically falls and it asymptotes. It's finally worth plotting it out. And I gave it data that it had to learn from is this particular data and find a function that would fit this. Right? Now, first pay attention to the left. You should always do it like this, guys. Do you look at the left? What do you see? Loss with steps, right? Loss with epochs, number of iterations, right? With the steps. And would you say that it has learned pretty much whatever it has to? No further epochs are needed, right? Loss is saturated. Now you look in the right-hand side and you look at this picture. Do you think the blue line has reasonable fidelity to what the data is trying to tell? Yes. Right. Now also observe that the blue line at this particular moment seems to be, if you notice carefully, made up of rather pieces of lines, piecewise, right? That has to do with something called activation function. That's another mysterious beast we'll encounter. If you choose an activation function which has linear parts to it, you get an overall approximation that's made out of little piecewise putting it together. But if you choose a different activation function, a smoother activation function, the curve would be smoother. Are we together? Right? You will get a smoother curve, and I believe I might show that in this lab. So this is complete batch gradient descent. Do you notice, guys, that the loss so nicely, it flattens out, isn't it? Let's see if we take mini batches. Same problem, same network. We go through mini batches. Do you see that for loop, and the famous equations I talk about? Results, the 4 lines of learning sitting inside the double for loop, right? That is it. That is the learning in machine learning here in a simplified way. Same thing. Now what happens? Let's plot it. Oh, did somebody ask, can we get trapped in a local minima? And we may think, okay, we have flattened out. What would have happened if we had just stayed at, let's say, 1,000 iterations, 1,000 steps, 1,000 iterations? We might have gotten the false or misconception that we have reached the bottom, isn't it? And does it give you evocatively a sense of this? When you look at it, look at how many false minimas are there, how many valleys are there way up in the Sierra Mountains that you can fall into and think you have reached the bay, the ocean, isn't it? So that is, in a very literal sense, you're seeing that happen, even in this simple example here. But eventually it falls out. But do you notice that in a batch, again, it's bouncing around. The errors are not averaging out to 0 because there is some level of misdirection in the small batch. Is varying you a little bit, of course, all the time. Much more bouncing, right? Here is your function, right? And now, what happens if you do stochastic gradient descent? One item at a time, right? Look at that. Now comes, oh boy, does it at all seem to converge? It sort of does, but it is just wandering around the right answer, isn't it? It's beating around the bush. So that's the price you pay. So the lesson to take away from it is that a good compromise is to go with mini batch. Right? The only question remains is what's the size of the mini batch? At the one limit, if mini batch size is 1, it becomes stochastic gradient descent. If mini batch size is the whole total data set size, it becomes batch gradient descent, right? But the point is, do you notice that I gave it a function, any function, and this network, without getting any hints, sort of molded itself and adapted to this function completely. Now, I would like to give you, and I would like to finish with another example, and that is it. And I will leave you with that. Can it approximate, this was too simple, a sine wave. Can it approximate all sorts of hard functions? Right? I say that neural networks are insanely smart. They can adapt to anything. So the first function I give it, original function I gave it is this, the same network. I ask it to do that. And by the way, you'll see all the code is there. look to the one on the right. Do you think that it has a fairly high fidelity to the thing on the left? The left is much smoother, of course. Remember, neural networks are approximators, right? They'll get it mostly right. But has it gotten mostly right? It has, right? Now, suppose we take a weird function. I tried to create a weird function. What did I do? I forgot. Oh, look at this. This is a function. I threw in some algebra. I threw in some trigonometry at it, right? Why not? And then I said, okay, go learn from it. And what do you think, guys? It still caught on to it. It's very hard actually for you.
Question here, Asif, again, sorry. In this function,
yes.
Right? So there is one clear minima, right? That we can see. Let's say if we had two that were approximately the same depth, this function would still have managed to bounce out of one and then.
No. See, you're mixing up with the data shape and the loss function minima. Remember?
Yeah.
Loss function is entirely different from the data.
I see.
Data is different. You're mixing up the loss function. That is why, hold that. I mean, I was a bit hesitant introducing the loss surface. We have a whole discussion for it next time.
Asif, how did you get the data associated with that weird function?
How did I create the data for that?
Yes, because you define a long weird function. Then how did you give the data?
Oh, because I generated it from the mathematical function. Just sampled off the mathematical function.
Go ahead. Question. So with this kind of a model, will there be a problem of overfitting at all?
This is for neural networks, right? This is not even kindergarten. It's like newborn play, right? It is too easy for it and it doesn't overfit.
Is there a problem overfitting at all in neural networks?
Oh, yes. There is a problem of overfitting. Remember, I talked about the double descent thing? Neural networks are weird, actually. They overfit, and then after a bit of more complex, you make your thing is, okay, this model is too complex. It has overfit. Let's simplify it. Actually, counterintuitively, you make the model even bigger, and then the overfitting goes away. That's a double descent mystery. Right? And we'll talk about that. See, when the time comes, this field is, if you really look at you understand it. See, people look from the practical, there's this thing came out, Sora came out, this ChatGPT came out. But if you look at the mathematical foundations, it's just elegant, it's beautiful. And there are lots of very interesting and exotic beasts in this forest.
So one question, maybe like you can give us a clarification on the terminology, the parameters. So especially when you talk about like the double descent, the number of data points.
How complex the model is. How complex the model is relative to the data set size and data set complexity. Right? See, it is not data set size, but what is the underlying dynamics that generated the data? So, for example, if SineX generated the data, and you start with a bizarrely big neural network, likely, at least in the early stages, you'll have overfitting. Right? That's it. Okay, guys, because you guys want to be left early, I'll just end with this. You can go on making complicated functions. So I think I did this, SyncX. Those of you who are into signal processing, you must be saying, you can't go away without doing SyncX. Well, here we go. Right? And then, to make life even more interesting, what if you write a bizarre function like this? How many of you feel that like it is easy to approximate this function? Let's see what this looks like. Sine of, pretty much sine of sine of sine of sine. Right? What does this look like? Look at this. The original function is this. The approximation is this. So you notice that you need a bigger network. If you take a bigger network, then it will adapt to it. Yeah. But you have to do that. I'll leave that as an exercise for you guys. And that's all, guys. Today, the lesson is, so the homework is, guys, walk through the code, understand what you can. Those of you who are new to Python, take your time. It will take you a month to get into it properly. Those of you who are familiar with Python, take a deeper dive into code, right? And those of you who have some idea of activation functions, go try out different activation functions. What did we learn today? Today we learned that networks are universal approximators. We learned that their ways to their details. We learned about two kinds of loss functions, one for classifier, one for regressor. We learned what classifiers are, we learned what regressors are. We learned about various methods of learning, batch, mini batch, stochastic, right? Learning. And that is it, guys. Next time, we'll learn the most important topic. How exactly does learning take place?
So Asif, if I can trouble you to go to that, those 4 lines that were, you said, at the heart of the learning, right? Which was that backward, and then there was a step.
Yes, let me go there.
Yeah, right at the beginning, the first example I think you showed us.
Yeah, not in this, in the other one. Yeah, the other one.
But pretty much every example should have that, right?
Exactly. No, but in this, because I didn't want to repeat the code, I abstracted it out into a function.
Okay, so this one was, so again, just Asif,
look at these.
So network is a function that you have written that we can look at similarly with loss function, backward, step, all of these you have written in the code that we can look at and try and understand?
Absolutely. See, the only thing I wrote is this code and this network, simple feed forward network. Do you see this?
Yeah.
That is all. And the rest of it, the framework gives. And because obviously at this moment, I want to keep all things dead simple. Where will you find this? You will find it in the SVLearn, in this. I leave you to search for it.
Simple feed forward is what you wrote, or is it what is there?
I wrote. Here it is. Here it is. Simple feed forward. Do you see? It is a network with actually only 3 hidden layers. Right? 3 hidden layers. That's it. And guys, if you are looking at it, the code looks unfamiliar. It will begin to look very familiar because there is no mystery to this code. It's straightforward.
Way too much sensory overload, sir. That's what.
Yeah. All right. So we'll close today. Huh? So next time, activation functions possibly, and gradient descent. We'll learn about how machines learn.
So firstly, hidden layers, knowledge of, we'll talk about it, right? How many do we?
All right, guys. So officially, I'll end today's session. Any big question on record before I close today? I know that you guys on the East Coast is terribly late, so I don't want to. I kept to a promise of 20 minutes. 20 minutes up. Anybody? All right. I'm stopping the live session. I hope you had fun, guys. I know that there are lots of guests, and here I hope if your intention is to just sample what AI is all about, I hope you're getting some